Hello everyone, they finally released the June 2024 Regents, so I'm going to do it. Like always, you can follow along with me, you can do it first yourself, whatever you feel like. So here we go, June 2024. Let's see how it goes. Alright, we're starting with the multiple choice. Part 1. The diagrams below represent the atmosphere and inferred interior structure of the planet Uranus, everyone's favorite planet. So the interior structure, anything to do with interior structure is going to be something to do with density because it makes these layers, but let's see what they have to say. Which two factors cause the layered structure? Okay, so we definitely want density, right? So there's density here, so anywhere else, density here, yeah. Okay, so one of those. What's going to make this certain layers get to the middle is going to be gravity is going to pull everything in. So gravity and density differences is going to be your best answer here. Period of rotation doesn't have anything to do with the interior structure. Okay, number 2, which process occurring in the sun? Alright, I automatically know it's nuclear fusion because that's the only process in the sun that's in the curriculum, so it's 4. Number 3, compared to the sizes of the planets and revolution of the terrestrial planets, sizes and period of revolution, the Jovian planets have what? Alright, so this one, if you don't have it memorized, you can go into your reference table, and you could go to page 15, right here, and you could compare. So, smaller size is shorter period of revolution, smaller size is longer period of revolution, larger size, longer period of revolution, and so on and so forth. So, as you can see, these big planets here have the longer period of revolution. These are in years. So just be careful. Like, don't think 687 days is longer than 11.9 years. So it's going to be larger sizes and longer period of revolution. Alright, number 4. The photograph below shows a dust-covered icy object that has a highly elliptical orbit in our solar system. So something that's very elliptical means that if this is the sun, it's going to be going like very elliptical, like very oval essentially. That's probably going to be a comet, and especially that it's icy. So number 1 looks good. Meteors don't have highly elliptical orbit. It's not a moon and it's not a planet, so that's a comet. Number 5, at which location will the sun appear to pass directly overhead? Okay, the sun only ever goes directly overhead between 23.5 degrees north, Tropic of Cancer, and 23.5 degrees south, the Tropic of Capricorn. That's the only areas there and in between that it could be. So we need to find which one of those places is going to be in that zone. So for this, you can go to your reference table. We're going to go to page 4 or 5. Doesn't matter which one. 4 is probably better because it's labeled. So it looks like Northern Australia is in that zone. Here's 23.5 south and 23.5 north. So it's got to be in the middle of that. So it's going to be Northern Australia. And you could check all the other ones. I just, I know it's the answer. The water layer of the Earth covers approximately what? So you just have to memorize this. It's 70% of the Earth's, like, here. Not inside the Earth, or not in the atmosphere. So the atmosphere is wrong. This is the sky. The water's not in the sky. It's on the lithosphere, which is the crust layer. Alright, number 7. That is a giant hole. Okay. What is this? That's a crater. Definitely a crater. And that was formed by like a big meteor or something that smashed into the Earth. So it's an impact event. 3. Alright, we have the central star Polaris. This is a time lapse. These are star trails. And remember, these are going to move at 15 degrees per hour because it's based upon how the Earth rotates. So Polaris does not appear to move because it's what? So Polaris, if you look at the Earth, it's tilted on its axis. Polaris is like here. It's directly above the Earth's north pole. So it's above the Earth's axis of rotation. 3. Number 9. Which location is the time 2? Okay, it says solar noon is occurring at location X. So in this case, they want us to assume that this is 12 p.m. So east increase, and it's 15 degrees per hour. So these are going up by 15. It's 30. Here's 45, 60, 75, 90. So 12, 1, 2, letter D. East, you go increase, west is less. That's how I remember. East increased, west is less. Number 10, how many degrees per day does the Earth move in its orbit around the sun? Well, it takes 365 days to go 360 degrees in a circle. So it's about 1 degree per day. All right, constellations. Anything to do with constellations is the Earth's revolution. We see different constellations throughout each season. So that's because we revolve around the sun. The Earth revolves around the sun, too. All right, we got a dew point chart question. What is the relative humidity? So I want to know what's the relative humidity when the air temperature, which is the dry bulb, air temperature is the dry bulb, and the wet bulb temperature is 11. So the first thing we're going to do is subtract these because that's the difference. So 20 minus 11 is 9. That's the difference. So now we're just going to go to air temperature 20, difference of 9 on the relative humidity chart. Relative humidity, air temperature 20, difference of 9 right here. And we're going to count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30. 30%. Is that a choice? Yep. Alright, number 13. Earth's early atmosphere consisted of CO2, water vapor, hydrogen, and nitrogen. During this time, the first crust formed and made of igneous rock. Based on this information, how did the Earth's early atmosphere form? This is just a memorized question. So volcanic eruptions erupted early on and spewed out all the gases that currently make up the atmosphere. So that's going to be 1. Number 14, it's giving us latitude and longitude, and it wants to know where the subtropical jet streams are. This is on the reference table. So we're going to go to the reference table here. Look, jet stream, subtropical jet streams, right there. There they are. So 1 is at 30 north, and 1 is at 30 south. And it also, so it's going to be either 1 or 2. It's not the 60s. And it's saying lower or upper troposphere. So we have to look at that. The tropopause is here. And the jet streams are at the top. So it's lower stratosphere, upper troposphere. So it's going to be upper troposphere. 15. The transfer of heat energy in the oceans due to density differences. So we got 3 methods of heat transfer. Remember, conductions through solids, convections through liquids, and it has to do with density, radiations through empty space, and insolation means amount of sunlight, so it's going to be 2. Which list of Earth's materials indicates an increasing order in the amount of energy needed to raise the temperature of them by 1? So this is specific heat. That's the definition of specific heat. So now it's saying an increasing order in the amount of energy. So we want the lowest specific heat first, and it's got to go to the highest specific heat. Okay, so we want these ranked from low to high, and we're going to go to page 1. And the reason we're doing it low to high is because in increasing order. So that means it's going to go higher and higher and higher as you go. So lowest out of copper, basalt, iron, or lead. Lead's at the bottom, so that's first. Then we got basalt and granite. Does that go in order? Basalt and then granite. No. So that's wrong. Iron, then copper, then lead. No, lead's at the bottom, so that's, I know that's wrong. Basalt, iron, and granite. Basalt. Nope, that goes out of order. It was the copper, iron, basalt. Copper, iron, basalt. That's the answer. Okay, which color and texture of surfaces with equal areas have the least temperature increase? So we don't want them to absorb. No absorb. So that's going to be light color and smooth. That's the best reflector. If it said the most, you would have picked dark and rough. Over the last 200 years, global warming is inferred to be primarily caused by what? It's an increase in burning fossil fuels like CO2 releasing in the air. Methane's another greenhouse gas. Water vapor is another greenhouse gas. So it's going to be an increase in three greenhouse gases. All right, we got 19. All right, there's an air temperature line and a dew point line. So what I know automatically is when the air temperature is hitting the dew point right there, that's 100% relative humidity. That means the air is fully saturated with water. So what is the day and time when precipitation will most likely occur? It's at that point, right there where they hit. So it's going to be Monday at like 7 p.m.-ish or 8 p.m. So there we go, 2. The United States below shows a portion of the Grand Teton Mountain, mid-July. Okay, so it's showing there's snow on the top of the mountain, and they want to know why. It's because mountains are tall. Elevation 1. All right. Which percentage of the radioactive potassium-40 in a sample will have decayed in that many years? Okay, I'm putting a star next to this question because this is tricky. It's mean. So normally, for radioactive decay, we just have to figure out how much decayed, how much burned away, how much is left. Sorry, how much is left. They reverse it on this one. So 2.6 times 10 to the 9th. All right, so let me show you what's going on here. Potassium-40, that takes 1.3 times 10 to the 9th to cut it in half once. So I'll do the work down here. I do a fat chart for this. If you don't know the fat chart, you could watch my video on radioactive decay. So at no half-lives, no time went by, and there's 100% of the material left. 1 half-life, there's 50% left, and 1.3 times 10 to the 9th years went by. We need to get to 2.6 times 10 to the 9th. So 2 half-lives would be 2.6 times 10 to the 9th, which means 25% of potassium-40 will be left. They didn't ask that. They asked how much decayed, how much broke down into the other substance. So it's going to be whatever is left over. So if there's 25% of potassium-40 left, that means 75% decayed. So that was mean. A lot of people picked 1 on that one because they didn't see that it's decayed. 22. Based on the geologic history of the Earth, which group of organisms existed for the shortest amount of time? Okay, let's see. Well, first, let's think. It's probably humans because we've barely been here, but we can go look. Geologic time scale. So birds, look, birds have been around for this many years. Dinosaurs here. Grass, I mean, grass is right here, and then humans barely. So it's humans. Oxygen first became part of the Earth's atmosphere from what? Okay, this is on here, right here. Oceanic oxygen produced by cyanobacteria. So we're going to pick something like that. Life process of cyanobacteria, too. Another reference table question. The letter X on the map shows the location of the present state of Florida. Okay. The position that is now Florida to have been positioned on the equator approximately how long ago? So we need to get that X on the equator. Again, another reference table question. So check this out. Look, here it is. So this is the Florida. Oh, no. Not that. That one. That's Florida. So we need that to be on the equator, which is right here. So that's right here, 232 million years ago. 3. So far, there's a lot of reference table on this. The division of geologic time into eras, periods, and epochs is based on what? So which one of these is most likely going to cause those to be changed? So it's nothing to do with magnetic fields. Mountain building events sometimes, occurrence of widespread volcanic eruptions sometimes, but it's mostly about the life forms. That's going to be your best answer. All right, we got an earthquake question. The first P wave from an earthquake was recorded at 10:20 at a seismic station located 2,200 kilometers from the earthquake epicenter. At what time did the S wave arrive? Okay, so we need to find the difference. So that's going to be our main thing. So 2,200, we're going to go to that. Okay, 2,200 right there. And we're going to say, okay, the P wave took about 4 minutes and 20 seconds. And the S wave took about 8 minutes. So that means there's a 4 minute and a 3 minute and 40-second gap. So there's 3 minutes and 40 seconds in between those two. So if it's 10:20, and then you have another 3 minutes and about 40 seconds go by, that's going to be about 10:23 and 40 seconds, approximately. I'm just doing this on a screen, so this is going to be the closest answer. It might have been 3:30 exactly, but I can't estimate it that good on my screen here. Which two hotspot boundaries are located at plate? Oh, which two hotspots are located at plate boundaries? Oh my gosh, so many reference table questions going here. Go to our hotspot. So you're going to look at these, and you're going to see which ones land on the line, the plate boundary lines. So I see Bouvet, Iceland, Easter Island. That's pretty much it, right? So let's see if that's one. Iceland, Easter Island, Bouvet. There we go, 4. 28, we got a meandering stream. So remember, erosion on the outside, deposition on the inside. So erosion is when it's really fast, and deposition is when it's slow. So deposition at sea. Instruments that record seismic waves on Mars allow scientists to infer what? Okay, seismic wave, that's earthquakes. So something to do with earthquakes or something to do with like plate tectonics. So earthquakes, seismic waves, helped us infer the interior of the Earth. So this is going to help them do the internal structure of Mars. The block diagram represents a landscape with 2 valleys. Okay. The two valleys most likely formed because the shale and the limestone bedrock did what? Okay, so it's pretty much saying, wow, this question is kind of tough. So the shale and the limestone here are lower, right, than these mountains here. So they're going to be less resistant to weathering than whatever this stuff was. This stuff's going to stick up and make the valley walls. So they're less resistance to weathering than this dot, which is sandstone and conglomerate. And this igneous rock is also making mountains over here. So shale and limestone are weaker than those 3, which is 1. So far, that right there was the hardest question, I think, so far. So we'll put a star next to that. Actually, that radioactive decay question was not hard. It was just like word trickery, but this one was actually kind of hard. 31. The photograph below shows rocks found in England. Okay, they're all round and smooth, so that's going to be abrasion. So water, essentially, when you have something in water and it's square and it rolls, it chips away the edges and rounds it out. Photograph shows a volcanic mountain, and they want to know the stream drainage pattern. So imagine this. It's raining on the top of this mountain. Some rain goes down this side, this side, this side, the back side, so you get something like this. I can't draw 3D, by the way. You got to use your imagination on that one. All right. We got a landscape feature. Ooh, this is a delta. I just know that automatically because this looks like a river and this looks like the ocean, and here's your like tree branch sort of looking structure. So that's a delta formed by stream deposition. It's dropping off everything in the ocean. What's the name and texture of a sedimentary rock composed of carbon? Another reference table question. We're going to go to the sedimentary rock chart and try to find carbon. Okay. Right here, carbon. Bituminous coal. That's the answer. Bituminous coal. Oh, then we need the texture. What type of texture? Go left. Bioclastic. See texture? So 4. Alright, we got the cross-section below represents an igneous intrusion into sedimentary bedrock layers. A, B, and C identified different rocks within the shaded zone of contact metamorphism. Which ones would most likely be found? Okay, so they just want to see what would this turn into, and this turn into if it was metamorphosized by an igneous intrusion. So we have to find what these three symbols are. Those are the symbols here. So you could see like this one here with the circle-y things, that's conglomerate. This is sandstone, and this is limestone. So the way you would see this is you would go to the metamorphic rock chart and you would read what turns into what. Like, look, low-grade metamorphism of shale. We don't need shale. But we do need sandstone, so we got quartzite. Look, this limestone turns into marble. And then metaconglomerate is what turns into from conglomerate. So this is going to be sandstone is quartzite. Then we got marble and metaconglomerate. So marble, quartzite, metaconglomerate. 2. Alright, let's see what's going on here. They're saying the Milky Way is going to collide with Andromeda in 4 billion years. That's going to be a fun day. The gravitational force pulling the galaxies together is influenced by what? So it's going to be 2 things. The bigger the thing, the more gravity it has, and the closer they are, the more gravity they have. So it's going to be the mass and the distance. 37. The Andromeda galaxy has a shape that's similar to the Milky Way. What's the shape? So it's going to be a spiral. The spiral is the most common galaxy in the universe. And there's billions of galaxies in the universe, so that's going to be 4. Alright, we got the water cycle. Beautiful. So we could just label these up. Evaporation, transpiration, this is runoff, infiltration, precipitation, and then condensations in the cloud. Okay. Which process is A? Transpiration. Which process and heat energy exchange are represented by B? B is evaporation. So 1 and 2 are out. And then to get this number, we're just going to go on the reference table and look. Look, vaporization means evaporation, 2,260. 3. Which conditions would cause runoff to decrease? So how do you get runoffs? Like flooding, essentially, and you want it to be less. So if there's going to be less flooding, less rain, definitely, so get rid of those. And then a decreased slope, because an increased slope would make it flood down the hill. So if you decrease the slope, make it flatter, it's not going to be running off. So it's going to be 1. Alright, couple things here. This is elevation shown in feet. Here's our steep area. This is going to be what direction the river's flowing, because the lines bend upstream. And I mean, that's pretty much it. 1,000 is up here, so this is uphill. And then there's a gradient here, so we'll see what they can ask. Which profile represents the shape of the land between A and B? Okay, it's just going to be going down a hill. It's a steep hill. So it's going to be 3. Whoops. Okay, it wants us to solve gradient in feet per mile from C to D. I'll do my best with the computer here. C to D. Okay, so first we got to get our change in value. So C is 1,000, and then D is on the bold line, which is 500. So it's 500 divided by the distance between C and D, which on this one you're going to have to... Do you have to extend the scale? Let's see. Yeah, so it's going to be probably like 3. I can't measure this on my screen, which is very annoying. Let's see if that works. So if you just do 500 divided by 3 miles, let's see what I get. That's just me eyeballing it, which I don't like to do. 166.6, is that an answer? Yeah. Okay, moral of the story there is I got lucky eyeballing it. I would not eyeball it. You're going to measure that, this scale here on a scrap paper and then put it up to the line and keep adding distance to the scale until you get the right line, but it was 3 miles. Okay. Letter X is located on which landscape feature? Let's see. Okay. This question is terrible. Okay. A sandbar is literally a mound of sand in the water. A sand dunes in a desert. So we're talking about a river here, so that's out. An escarpment is like a cliff, like a cliff near an ocean side, and then a floodplain is like an area next to a river. So that is going to be an area next to a river. That essentially, when it rains a lot or when the water overflows, it floods this area and this area. So it's going to be 4. Okay. The arrows on which map best represent the direction of stream flow relative to the pond? So we already did this. The stream's going to flow this way. So relative to the pond, it's going like this, northeast. Let's see if that's an answer. Yeah, it's going to be 3. Okay. We got subduction. So there's 3 choices, A, B, and C. Compared to the density and thickness of continental crust, the oceanic crust is what? So there's a hint for this on the reference table if you go to page 10. Right here. Granite is continental and basaltic is oceanic, and then it shows their relative densities. So the continental crust is less dense than the oceanic crust. So the oceanic crust is more dense, and then the thinner and thicker part you have to remember. So oceanic crust is thinner. 3. Which diagram represents the motions at plate boundary B, which is going to be here. This is going to be oceanic, oceanic. So they're going to crash into each other. This one's subducting under this one. So this one, 3. Which surface feature is created at plate boundary C? So this is continental, continental, which means a mountain is going to form because it's going to go up. So it's going to be 4. Alright, let's see. So Petoskey stones. Okay. Petoskey stones are famous rock specimens found on all beaches of Lake Michigan, but especially on beaches near the city of Michigan. The stones are well-eroded pieces of coral reefs that were alive between this age. That might be important. Coral reefs, that might be important. At the time the coral animals were living and forming the reefs, the area was underwater and the coral, along with many reef animals, thrived. Eventually the ocean disappeared and the fossil reefs were uncovered, advancing and retreating glaciers. That's interesting. Broke off pieces of the reefs, smoothed their edges, and distributed them throughout the area. Lake Michigan's formed at the end of the Ice Age. Okay, today lake waves continue to distribute an endless supply of these stones with fossils. Okay. The coral that eventually became Petoskey stones were alive during which geologic time period? Okay, right there. 375 to 400 million years ago. We need a time period for that. So we're going to go to our time scale and go to that spot. Right here, 375 to 400, which is right here. It's the Devonian. Which New York State Index fossil is in the same group of organisms as the stone coral? So it's going to be coral. Which one of those is coral? Wow, so many reference table questions. So we're going to go here. Corals, right there. So V, U, or T? This one, V, U, or T? Lycaria, cystophyllum, or pleurodictum? There it is. The stone as shown in the photograph is classified as what? So it looks like, so we're going to need a size. That's going to make these right. So from here, and they give a ruler, it's about 6 centimeters. And we're going to go to our another reference table right here. 6 centimeters, particle diameter is going to be 1, 2, 3, 4, 5, 6. Because here's 6.4, so it's a pebble. Okay. Oh, yay. We graduated. We're on short answer questions. Okay. Let's press on. From 51 to 54 on the weather map in the answer booklet. We got our answer booklet right here. There's our weather map, I guess. On the map, draw the 1000 millibar and 1004 millibar isobars. Extend them to the edge of the map. Okay, here we go. Ready? 1000. Edge of the map. 1000. 1000. 1000. And then 1004 is going to be between 1003 and 1006 to grab this one. Below the 1005 to get that one. Between 1006 and 1002. That's your answer. Convert the air pressure of the lowest value isobar shown on the map from millibars to inches of mercury. Okay. Let's see. Lowest value here is going to be 984. So we're going to convert 984 to inches of mercury. And again, another reference table question. Let's go to the conversion right here. 984 is right here. So inches of mercury is going to be, here's 29.00. 29.05 is probably close enough. So we're going to put 29.05. Okay. 53. Identify the weather instrument for air pressure. So that's just like literally rote knowledge. That's a barometer. You just have to remember a barometer measures air pressure. 54. Write the two-letter symbol of an air mass where this is in the hurricane form, where the hurricane formed. Look, Florida. So hurricane forming around Florida. That's going to be maritime tropical. Maritime means it's near water. Tropical is warm. So MT is your best one for that one. 55. They want something in degrees Celsius. Let's see. Using garnet as a geothermometer. Okay, a geothermometer mineral is a mineral with slight differences in composition that can be used to estimate the temperature at which some types of metamorphic rock form. Garnet's a geothermometer mineral because there are several types of garnet that contain different amounts of iron and magnesium. The garnet coefficient indicates the ratio of iron to magnesium found in the garnet. When the garnet coefficient's high, there is a greater percentage of iron compared to magnesium. The garnet coefficient is an indicator of the temperature at which the rock formed. Okay, fine. Determine the rock formation temperature of a rock sample with a garnet coefficient of 1.55. Okay, so we're just going to find that. That'd be in here. It's between 1.47 and 1.63. So the answer is between 640 and 590. So I'm just going to pick 600. So that was easy. That's just reading the chart. There's nothing, you don't have to know anything about what a garnet coefficient is. It's just like a reading. So describe the rock formation temperatures that are indicated when the higher garnet coefficient is found. Describe the rock formation temperature. So it's going to be, here's your temperature. Higher coefficient, lower temperature. See, lower one is higher, so it's going to be the temperature is dropping. Uh, 57. Identify one foliated metamorphic rock for which the garnet coefficient might be used to determine which temperature the rock formed. Okay, so we need a foliated metamorphic rock with garnet, right? So we're going to go to our rock chart. And we're going to find metamorphic rock. And we needed to have garnet, so here's garnet. So we could pick phyllite, schist, or gneiss. I will write schist because it's a good rock. Okay, going on to 58. Alright, we got a map of Australia, and we're showing the locations of 3 cities, Brisbane, Melbourne, and Wagga Wagga. The graph shows the average monthly temperature in Wagga Wagga and Melbourne in degrees Celsius. Okay. Where? Oh, there we go. Compared to the average monthly temperature curve of Melbourne, describe how the curve is different for a city in New York. Okay, so we are not in the southern hemisphere, so we are in the northern hemisphere. So what that's going to mean is we get our highest temperatures in June and July in our summer, and our lowest in January and December. So it's going to be like a New York one would be like this, right? So it'd be completely reversed. So that's going to be my point that I'm going to write. So I'm going to say it would be the hotter temps in July, and that's all I'm going to say. That's it. That's all you have to be able to do. You could just say the opposite too. It would be colder temperatures in January. That's fine. All right, circle one warmer cool current and name the ocean current. Let's see. Circle the warmer cool to indicate the temperature of the ocean current that flows off the coast of Brisbane. So we're going to look at Brisbane. So that's the east coast of Australia. So we're going to go to our reference table. We're going to go to page 4, our ocean currents. Find Australia. Look, it's the East Australian current, and that's a solid arrow, which means it's warm. So warm East Australian current. All right, base your answers to questions 60 through 62 on the cross sections below and your knowledge of earth science. The cross section below represent the changes in the land of Montauk Lighthouse between 1838 and 1988. So right there, you can get your calculator and subtract that out, and that is over 150 years. So that might come in handy later. And it's built on unconsolidated sediments located on the eastern tip of Long Island, and there's an edge, the distance from the lighthouse to the edge of the escarpment is located in the cross-section. Escarpment's like the cliffside edge. So identify one agent of erosion that removed the sediment and changed the position of the escarpment. So I would say the waves from the ocean is going to be the most substantial difference. So we could say wave action. Okay. Calculate the rate of erosion in feet per year from 1838 to 1988. All right, so we know that's going to be 150 years, and we went from 220 to 100. So you're going to set it up 220 minus 100 feet divided by 150 years. So you just plug that in your calculator. So 220 minus 150, nope, 220 minus 100 divided by 150. So you're going to get 0.8 feet per year for that one. And then 62. Describe one action that can be taken to slow or prevent the erosion of the land between the escarpment and the ocean. So if you wouldn't want this to be eroded back, I would build like some sort of wall in the ocean that would kind of like eat the waves, essentially, to stop the waves. So I would say build some type of wall. You could say like build a jetty. That sounds good. Oh boy. My favorite thing ever. Do we have to graph something? Oh my gosh. Alright, what are we graphing here? So June 22nd in Rochester. That's close to the summer solstice. Let's say on the graph, construct a line graph applying the altitude of the sun for each time of day shown in the data table. Okay, the altitude of the sun for each time of day. So we're doing this one. So 9 a.m. is 35. 9 a.m., 32, 34, 35. And you're going to be more accurate than me. Remember, I am on a screen and it's really hard to do this. But I'll try my best. 10 is 46. 11 is 56. I'm just going to make it a little dot and I'll go at the end. 12 is 65. Okay. 1 is 70. 2 is 68. 3 is 60. 4 is 50. 5 was 40. And 6 is 29. Okay, I can make all these bigger. And it wants us to connect them. I'm going to do my best. Good enough for me. Okay, great. Based on the data, describe the relation between altitude of the sun and length of the shadow. So altitude of the sun is low, length of shadow is high. Altitude of the sun is low, length of shadow is high. Altitude of the sun is higher, length of shadow low. So it's inverse. As altitude of the sun increases, shadow length decreases. So you can write indirect, inverse. Some people write like negative relationship. So you could write it all out too. You could say as altitude increases, shadow length decreases. Okay, 65. Determine the shadow length at 4:30. Okay, 4:30 is between 4 and 5. So shadow length is between 4.1 and 6. So I just write 5. Right? Is there an actual pattern here? Oh, I'm not doing this right, guys. We have to base it off of the graph. They gave you it. Look, I probably just got lucky. 4:30's here. We're literally right there. So it's 5. I got lucky. So I was estimating off this table. I didn't know that they plotted it in the booklet. But I got lucky. Okay, 66. Okay, there is an unconformity, rock layers, a fault, index fossils. Let's see. Identify the geologic time period which unconformity WX was forming. So it's forming between this bird and this coral. So we need to find the bird and the coral on the time scale. K and V. Between K and V. K and V. So it formed in this one. So that's the third box above the bold line for me. Silurian. Yep. That's how you do it. Technically, it could also be Devonian and Ordovician because it's still in between that area, but Silurian is just the most obvious to me. I'm going to write that. Okay, in your answer booklet, circle the term that best describes the age of fault YZ compared to layers G and H. So YZ cut through G and H, so it's younger. So I'll describe the evidence that infers it. It moved them, so G and H had to be there before it could be moved. So it's going to be younger. And you could say G and H are faulted. That's pretty much all you have to say. Since they're faulted, they had to be there before it can be faulted. Oh no. Don't tell me I got a graph again. Wow. In the grid, I'm just going to read because it's just plotting points. Plot the positions of stars 1 through 6. Record the star number of each star beside the plot. In order to create, this is weird. In order to create the correct shape, connect the plots with 2 lines. The first line connects 1, 2, 5. Oh my gosh. Okay, so we're connecting different dots. So let's just label the dots, and we'll connect them at the end. So what do they want us to do here? We got longitude and latitude. Longitude and latitude. So this is our X, and this is our Y. Okay, Deneb, let's go. 20.745. 20.7 up to 45 is there. So we're going to put a dot and go 1. 2. 20.340. 20.3, 1, 2, 3, 40. That's 2. 19.845. 19.678, 45. 3. I can't believe they're having to do 2 graphs. That's crazy. 20.834. 20.834. 4. This is weird. 2035. It's like easy to mess up. 5. 19.528. 6. Alright, and then they plotted 7 for us, so that's good. Now what do we have to do? Connect 1, 2, 5, 6. 1, 2, 5. Okay, so this is just a line. Connect 4, 2, 3. Is that another line? Oh my god, that line was awful. Okay, there it is. Identify the planet in our solar system that has a period of revolution most similar to the dust cloud orbiting Tabby star. Let's see. Look, 700-day period of revolution. So we need to find the planet with about that. On page 15. Period of revolution, 700 days, Mars. It's closest. Okay. On to 70. State the name of the shortwave energy that's most likely blocked out by the dust cloud. Astronomers observed that a portion of the electromagnetic spectrum have a wavelength just shorter than visible light. So to get the one that's just shorter than visible light, we have to go to right here. Visible light, just shorter. There it is. UV is going to be the answer they're looking for. So far, this is pretty easy, I'm not going to lie. Like, I haven't seen it. We'll see how the rest of this goes. We're already on question 70. I haven't seen anything weird. It's a lot of reading and graph analysis and, like, reference table stuff, but nothing is, like, crazy at all. Alright, 71. Complete the table in your answer booklet by identifying the color and classification for 2 of the stars in the constellation of Cygnus based on temperature luminosity shown on the graph. Huh? Oh, Alberio and Tabby star. What am I missing here? Alberio and Tabby star. Okay, let's go and see what they give us here. Alberio, Tabby star. Oh, okay, look. Temperature and luminosity is there, and then temperature and luminosity is there. And they want to know what? The color and classification. Okay, so let's start with the Alberio. 4400, 950. 4400 temperature, 950 luminosity. Go here. 4400 temperature, which is like here. 950 luminosity. 950, which is up here. So this is going to be a giant. It's going to be a giant, and it's going to be between orange and yellow color right there. I'll just write yellow. Okay. And then Tabby star is going to be 6,201.5. 6,200 right here. 1.5 is a little bit here. Main sequence, and it's going to be like yellow or yellow-white. I'll write yellow again. I don't know if it's taking like yellow-white. Okay, well, look what I did wrong. I would actually get this wrong because I literally put the color in the wrong part of the table. Oh my gosh. So this is going to be... good thing I caught that, because literally that would be wrong on the regions. That's because I'm rushing. Wow, that was pretty bad. Anyway, ignore that. Alright, 72. Identify the 2 fronts represented along line XY. XY. Why does I say 2? Did I just read that wrong? 2 fronts represented along XY. Oh, there are 2. So we got these opposite ones, and this is just one. So if you don't know your fronts, you could go here. And they're right here. So opposite side's stationary and the other one's cold. So we're just going back. This one is kind of tricky, honestly. Tricky, not hard, but you just had to like sleuth for that one. You had to go in the data table and find out, and then go to the reference table and then put them in the table. So that one's kind of like a little bit more involved. 71. All right, 73. Identify the direction towards which the low pressure system just located south of New York State will move. Follows a normal storm track. Okay, normal storm track means everything is going to go northeast across the United States because we're in the prevailing westerly wind belt. See? Everything's going to go northeast. So it's going to be northeast. Oh, I get a little station model. That's fun. Complete the table by filling the values of four weather variables that are represented by the station model. Where is the station model? Is it this one? I guess it's the only one. Okay, cloud cover, none. Now, if you don't know where these things are, you could just go to your little station model cheat sheet right here, and it tells you what everything is right here. Air temperature is going to be in the top left. That's 46. Dew point is in the bottom left. That is 37. And then this says 217 for the pressure, but remember, this is a 2, so you got to put a 10 in front. It's going to be 10, 217, and then put a decimal between the last two numbers. All right, going on 75. All right, we got this weird map. Okay, it shows where the total lunar eclipse. Map 1 shows where the lunar eclipse was visible. Map 2 shows where the solar eclipse was visible. Okay. Great. Let's see what it says. Determine whether each of the eclipses shown on the map were visible or not visible to observer in Hawaii. Okay, so Hawaii is labeled right there. So it says it was visible, so it is in the lunar, but Hawaii is over here for the solar, so no. So yes to lunar, no to solar. Easy. On the diagram, place an X on the moon's orbit to indicate the position on September 7, 2025. Look, September 7, 2025, it's a lunar eclipse. So to get that, lunar eclipse, we want it to be over here. Solar eclipse is over here. So lunar eclipse is on the opposite side of the sun. Alright, state the number of degrees Earth's axis is tilted. Okay, we're tilted 23.5 degrees. That's just a memorize. It's also equivalent to the Tropic of Cancer, Tropic of Capricorn. Explain why a focal pendulum located in the Arctic Circle appears to change directions as it swings. Focal pendulum is proof that the Earth rotates. So the focal pendulum would never change if the Earth did not rotate. Earth rotates. If you would have accidentally written Earth revolves on that one, you would get it wrong, because focal pendulum only proves rotation. Alright, finishing up, 79 through 81, we got a block diagram. This is magnetic field lines. They're mirror imaged. Let's see. Determine the age and the magnetic orientation of the seafloor located 80 kilometers south of the ridge center. 80 kilometers is going to be, so 50, 60, 70, 80 is 2 million years old. Was that it? 2 million years old. Okay. And then the polarity of that section is going to be this grayish area, which is normal. Easy. 80. Identify the two plates that are diverging at the southeast Indian Ridge. Okay, so that's going to be on the reference table, page 5. Southeast Indian Ridge. Find it. It's right here. The plates are going to be the Antarctic plate and the Indian Australian plate. I couldn't have picked shorter names for me to write. Okay, we're on question 81. Explain in terms of cooling rate why the crust forms at the ocean ridge is most likely basalt. Okay, so cooling rate, basalt is extrusive igneous rock. So it cooled fast. because when that lava touches the ocean water, it just cools instantaneously. So, fast cooling rate. That's literally all you have to write. Basalt is extra. You don't even have to write this part. But that's what I would write. Okay. 82. Identify the chemical composition of the quartz that makes up Herkimer diamond. Okay, that's really easy. It's another reference table question. Go to quartz. Chemical composition, it's right there. SiO2. '83. Identify one characteristic of a diamond other than its color that allows it to be used in jewelry. Oh, Herkimer diamond. It's made of quartz. Sorry, I'm skipping the fact that it tells you what a Herkimer diamond is in here. I already know what a Herkimer diamond is. I didn't really consider that. They're actually quartz crystals. So another thing that makes it really good, besides its color, it allows it to be used in jewelry, it's super durable. So its hardness. Quartz has a really high hardness. I'm pretty sure there'll be multiple answers for that. You could say crystal shape, its luster, stuff like that. 84, an orogeny. Identify the orogeny that was responsible for metamorphosis of bedrock now exposed in the Adirondack Mountains. Okay, so it says it's 500 million years ago. So right there, we're going to go on our geologic timescale and go to 500 million years ago, which is in this Cambrian period. We're going to go across. Is there an orogeny around here? Am I in the wrong category? No, it's the bottom of the Cambrian. So I see the Taconic orogeny here and the Grenville orogeny. So what am I missing? Let's read the question again. Oh, in the Adirondack Mountains. Look, Grenville orogeny in the Adirondack area. So it's probably the Grenville orogeny because of that. Grenville, an orogeny just means that a mountain was built, like a really main mountain was built. But that was just a timescale question. It's kind of weird though, honestly. I didn't really like that question that much. 85. In your answer book, last one, circle the term that describes the age of the Herkimer diamonds compared to the age of the Dollstone. Explain how the evidence cited in the reading supports your answer. Use the term Herkimer diamonds and Dollstone in your explanation. Oh my gosh. Alright, let's see here. The Herkimer diamonds, of course, are double terminated and found within outcrops around the Mohawk River Valley. Dollstone was formed about 500 million years ago in a shallow sea. While buried, cavities were formed in the Dollstone by the slightly acidic water. As sediment buried, crystals grew in the cavities, creating the quartz. Okay, so the Dollstone has to be older than the quartz because the quartz was formed from the ocean water going into the Dollstone. So is that what it wants us to say? Yeah. Okay, so the Herkimer diamonds are younger than the Dollstone. The ocean water goes into the Dollstone to make the diamonds. That's what I would say. All right, that was the whole thing. So overall, I would probably rate this one like a. It had a lot of reading, honestly, associated with it. But I would say this one was like medium. It wasn't bad. I thought it was all right. If I was a student, I would say this was a good one. It was a lot of, you were able to figure out a lot of stuff out like off the cusp. Like you didn't really, you know, you could figure out charts and read tables and stuff like that. You could get the question right on a lot of them. A lot of reference table. Anyway, thanks for sticking with me, and I will see you on the next video. Later.